the periodic table. Now there are a bunch of elements in the world where different substances. There's gold, there's silver, and also bronze, which would be when copper and tin together, that is bronze. So a bunch of substances. Some can be put together like copper and tin, that becomes then bronze. Or just gold or silver or platinum or something else. All these elements, they have to be sorted, and 109 are known in this book when this book was written. A few found since then. A few were found since then. Now, these 109 elements, they have to be sorted. They have to be sorted in some way. And the periodic table is the way to do it, which is a way which is often used to do it. And there was Dmitri Mendeleev, and in 1896 he published his idea how to sort them. He took every element which he knew about, without all the information down on the card, sorted them and published it then, and that was his result. So all the elements down, 1, 2, 3, 4, 5, 6, and so on, all the elements, 109 down in these lists. These lists are the periods, and that are the groups. It's like that. And they all have similarities, and someone who understands, is like that written in the book, how they are sorted there, can, by just looking at where they are written, know something about how this element will behave alone or with another one together. And now it is like that. There are different groups. There are the alkali metals, and then the alkaline earth metals, the transition metals, the lanthanides and austenites, and then the poor metals, the semi-metals, and the non-metals, and the noble gases. So all these groups. And they behave almost all similar if they're in such a group. So if someone understands it, they know it is written in the first group or the second group, that element will behave like that. It will burn at that degree, it will make then fire, it will react with other thing strongly, it will make something, it will shatter, it will make it going away, so it will make a solution out of it. How it will behave, basically. What will it do with another stuff? Will it be just peaceful there, or will it react? And for example, all these metals together, they have something similar things. Metals, they are solid at room temperature, a part of mercury for some reason. So solid, they conduct heat good. That is why if someone touches a metallic thing, it feels cold because warmth is going fast away. And other things, they are not like that. It goes not so fast away. Air, for example, is gas. And gas is not transporting the heat so fast, and also does not conduct the electricity so good. But metal does, and that is why cables are out of metal and stuff like that. So someone who understands it knows metal stands there and there and there, and they know out of that could be done a cable, or that stuff will react together with that, and so on. So something's there. How they are written there? Where is then written for carbon, for example, is 6 at the top, and then the C, then carbon, and then 12. The 6 means it has the atomic number 6. So someone could say atomic number 6 is carbon, or carbon has the atomic number 6. And that means that carbon is the 6th element in this list. There's 1, 2, 3, 4, 5, 6 somewhere there. And that 6 is the amount of protons in the nucleus. Such an atom has in the center of the nucleus, and then around it, shells, called like that. I don't think they're actually existing, but it's just called like that, shells, and on these shells are the electrons. So such an atom looks like that. In the center there is the nucleus with a proton in it by the atomic number carbon, 6. And then out of them, on these shells, however that now actually looks with these shells, there are now 6 electrons. So the same amount of protons has such an atom as electrons. And atomic number 6 says 6. Gold has whatever, 64, whatever. That means now 64 protons are in there, and the lead has 79 or whatever, and there are now 79 protons in the center and 79 on the outside. And these shells were starting like that. They're first a shell of 2, and then there are 2 electrons are on it. So that is for hydrogen. Hydrogen has the atomic number 1, and then helium number 2. Hydrogen has now 1 proton in the center and 1 electron then on the shell. Helium has now 2 protons in the center and 2 on the shells. And that is why we are so far apart written, because the shell is already full. I think that is the reason. So it doesn't look completely like rows, because these shells are differently. The first shell can only hold 2 electrons, the after ones 8, and probably even more. And so they're not written like 1, 2, 3, 4, 5, 6, 7, 8, or 10, so 1, 2, then 3, 4, 5, 6, 7, 8 or something like that, and then more or less like rows. And all the one in the first row, they have 1 electron on the outside. And the last row, there they have 8 or full. It wasn't said directly in the book. They are the electrons been full on the shells. Now, and that has a lot to do with how they react. Some electron with one on the outermost shell. If there's 1 electron on the outermost shell, that can easily react with another substance as if there were 2. So it has an influence how many are on the outermost shell, because that electron can be lost or gained. 1 electron can be gained to an atom and lost. So where they are, tells them how they are reacting, because all the one in the first row have one electron on the outside. That one electron, which is there on the outermost shell, so there's the nucleus with all the protons in it and neutrons also, and then all the electrons on the outermost shell, and all elements in the first group have one electron in the outermost shell. And therefore all these atoms in the first rows, these alkaline earths, have a similarity how they will react with other metals because they have one electron there. It's like a puzzle piece. That puzzle piece will fit together with south one who has 4, 3, 5 or 6 electrons in the outermost shell. And we're going always up. Every one further, one group further, or one row further, it's not said so directly here, as in one more. So one electron outermost shell, 2, 3, 4, 5, 6, 7, 8. So that is why there can be something read about how it all works. And maybe some interesting fun fact would be, the more protons are in the center, the more we're pulling in the shells. So actually the amount of atoms increases down the period with 15, 16, 17, 18, 19, 20 and so on, but the atom decreases in size because there are no more protons in the center pulling in the electrons on the outside. As a little fun fact. Now, and that is according to Susan McKeever's Science Encyclopedia book, written on page 32 and 33. Hi and welcome. I'm trying to learn chemistry today, the periodic table. After we've done it, we're going to do hip training. And if you participate in the hip training, then it's already on risk. And we read it in the previous, I think, 3 parts completely. And now we're going to go over it again. And we try to pass a little presentation about what was said here together. So the periodic table, this complicated looking table is really a simple list of all the elements. So there's a list of all the elements. They are arranged in rows in order of increasing atomic number or number of protons in the nucleus. So all these rows are going down, and the one further gives when an atomic number of 1 bigger, which equals also the atomic number, the amount of protons in the nucleus and the electrons on the shells. During the 1860s, chemists noticed that certain groups of elements behaved in similar ways and tried to set the groups out clearly in a table. In 1869, Dmitry Mendeleev published the best table, which is still used today. A chemist can tell a lot about an element just by looking at its position in the periodic table. Okay, we're going to start with that. In the 1860s, people who knew things about chemistry noticed that some elements were behaving similar to other ones, and they tried to make a comprehensive or good list which would not just list them down, but have them then in a good list together. In 1869, Dmitry Mendeleev had an idea for one, and that is where today used by most people. So Dmitry Mendeleev, he was a Russian school teacher. Dmitry Mendeleev collected all the information about the known elements and wrote out a card for each one. Then he arranged the cards in the order of the atomic weights to create a periodic table. He left gaps for elements he predicted would be discovered, and the 3 found in his lifetime proved him right. In order of the atomic weight. What is the atomic weight? Do they say that at some place? So let's take that back in mind. He ordered them based on the atomic weight. But the other things do we know? He made cards for each element and wrote down what he knew. And if there was one, and he also predicted where some elements were not yet known but later found, and for 3, which his prediction where they would be was even right. And also for the following one since found when it proved also right as far as it is to my knowledge. Okay, let's read the left down here. C carbon 612. So the atomic number is the number of protons in the nucleus. It goes up 1 by 1 along each period. So carbon 6. Okay, carbon has the atomic number 6 and therefore 6 protons in the nucleus. That is why carbon is 6, atomic number 6 by carbon. So then the C. The symbol is a shortened way of writing the element used in chemical equations. Carbon, for example, has the C. Some are based on other languages or something else. That is why they're sometimes quite complicated. But this is the shorthand writing for what they mean. The relative atomic mass is the mass of the atom compared with the mass of carbon-12 taken as 12. That is far too complicated to understand, and from that I know some things more, but I don't really understand it, so we stay away from it. That is just the relative, the atomic mass. Maybe we're going to make it as simple as possible, the atomic mass. I don't know directly how we should find what it would be. It seems to be, it's not doubled every time. So I don't really know how we come to it. It is compared to carbon 12 if there are 12 of them taken. We're going to stay with the atomic mass. So okay, then wegen the alkali metals, then the alkaline earth metals, then the transition metals, then the lanthanides. We have listed them down here. They would be between here 771. And the estinides, poor metals, the semi metals, the non-metals, and noble gases. I think that is too complicated. We want to make a video in which people understand the periodic table, not every small thing. So we're just going to say the alkali metals are on the side, then the alkaline earth metals, and then over to the other side, then the middle transition metals, and then on the other side there are then the semi metals, non-metals, and non-noble gases. So that people understand an overview, but I don't think it is helpful to just list them all. Groups and periods. How does the periodic table work? The 109 known elements, when the book was written, are arranged in horizontal rows called periods. These are the periods, these are the groups. The atomic number goes up as you move across. The periods start with an alkali metal on the left and end with a noble gas on the right. The atoms of one element on the left at the beginning of each period have only one electron in the outer shell. At the end of a period, the outer shell is filled with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9 are listed here as groups, but it doesn't have to be indicating for the 8. Are it always maximum 8? Let's take here lead, 6 shells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. These are far more than 8 electrons. So what do we do now? It's not that they're wrong about that, it's just that they are obviously not every time right about it. But I don't really know the rule, when the rule is right and when not. So we're going to just stay away from it. But it's a bit sad because that is an important thing, how many electrons they have on what shells, and there are rules for it. I just don't understand it now why lead has more. Or lead is here 82. Okay, we're going to stay just away from that one thing with electrons, how much okay. The vertical columns called groups each contain elements that have the same number of electrons in the outer shell. Or we just quote them. I don't really like to. But at the end of the period, the outer shell is filled with the vertical columns called groups, so we call it periods and groups, each contain elements that have the same number of electrons in the outer shell. On all these vertical down groups, they have all the same amount of electrons in their shell. And we have to explain the part with the electrons and having shells also. So maybe you're going to save it also. The periodic table. Group 40 would be carbon, silicon, germanium, tin, and lead. Period 3 is sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Okay. Metals and non-metals. Most of the chemical elements are metals. The non-metals are in the triangle on the right of the periodic table. I can't really see the triangle. That would be here, the non-metals. But it's not such a perfect triangle. So I don't know. We're going to say the thing with the alkaline earth metals and the semi-metals, non-metals, and noble gases. That is enough as an introduction. There are several big differences between metals and non-metals. Metals are solid. The only exception is mercury liquid. They conduct heat and electricity well and usually have high melting and boiling points. So we're going to say it. And they have similar, what is it called, characteristics? Characteristics, it's called like that. For example, all these metals when together, they are all solid at room temperature, except for mercury. They are usually solid, having a high melting point, a high boiling point, and conduct heat and electricity good. So I think that is a good idea, just to say it. And they form positive ions, cations, when they bond with other elements. It's too complicated without explaining the rest. We keep it back in mind if we get into an explanation. Otherwise not. Most nonmetals are gases with low melting and boiling points. They are not good conductors except for carbon. They form negative ions when they bond with other elements. We're going to explain the metals. That is something good to understand. Down a group. In some groups, such as group 1, the alkali metals, group 2, the alkaline earth metals, and group 18, the noble gases. The group relationship is very obvious. The elements are similar in appearance and reactivity. In other groups, such as group 14, the chemical properties remain similar, but the elements change from a non-metal at the top to metals at the bottom. So we have, for example, the metals, and they then mostly blend together. There can be some exceptions. In the group 14, for example, down, it goes from a non-metal to a metal at the bottom, from carbon to lead. From carbon over a half metal, silicon and germanium, a semi-metal, silicon and germanium. So there can be differences, but the metals are all together. They are on the top left. They sit here on the right of the periodic table. Yeah, what is it? That is the right, okay. On the right. Down a group, the number of shells increases by 1 with each element. So every group down there's 1 shell more, that is good. An atom can have up to 7 shells, and they can have up to 7. 1, 2, 3, 4, 5, 6, 7. The number of electrons in the outer shell is always the same as the other elements in the group. And the groups were down. The number of electrons are always the same in a group down. There can be up to 7 of them, and the amount of electrons in the last shell is the same as all the other ones of a group. Okay, that is good. Across a period, going across a period, the number of electrons increases by 1 with each element, and the chemical properties of the element show gradual change. In period 3, the elements change from metal sodium through the semi-metal silicon to the non-metal argon. The elements change from forming cations to forming anions. That is a bit too complicated. Decreasing size. The number of shells remains the same across a period, so same and always 1 more. Same period, 1 more group. But as the number of electrons increases, the size of the atom decreases. Okay, that is something interesting. We're going to see it because there's more. This is because the extra protons in the nucleus pull the extra electrons closer in it, so the atom is smaller. The more electrons and protons it has, the more shells. Okay, we don't have time left, but we are through. Sodium from group 1 has 11 electrons with 1 in its outer shell. Magnesium from group 2 has 12 electrons with 2 in the outer shell. Aluminium group 13 has 13 electrons with 3 in the outer shell. Aluminium there, 13. Silicon group 14 with 4 in the outer shell, so always 1 more in the outer shell. Phosphorus 5, sulfur group 16, 6, chlorine 7. Argon with 8 electrons in its outer shell. Yes, argon, but what is about lead? Because lead has 6 shells, and in the second one it has 16 or something, or 18. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. Okay, we read it, and I think we understood everything which we explained. We didn't explain the thing related with the cations and anions, and also not. Have we now 8 in the last shell? Lead obviously not. So 1 to 2 questions are left, but I think we have answered a large amount, and in the next video we are trying to make the presentation and saying it all. So if you were here for chemistry, you can go directly to the next part of chemistry, where we try to say all which we understood, which is almost everything, in a video where we're going to explain what the periodic table is. If you stay here and participate in the Hiptraining, then it's with your own risk. The feet are standing together, out with 1 foot and the other foot. And the heels and foot again. So toes down. As far as you can go. And then back in again. Stay down in the knees this time. And up again. And a bit apart, down to the knees, flex the legs, press them together, straighten 1 leg. And the and bend it again. And now the other leg, straighten it. And bend it again. And up. A bit further apart, down into the knees, flex the legs, press them together. Over to one side and the other side. Middle and up. A bit closer together and press to the outside. And one leg up to the outside. Breathe in. Middle and down and the other leg up to the outside. Breathe in. Out, middle and down. Leg to the side and lift it off the ground and place it again onto the ground. And the other foot. We need more exercise to move. One hand on tummy, one on lower back, and lift the leg up in a straight line. Try to bring the leg higher and pull the toes in. And pull the leg up. Upper leg. And pull the leg up. And over. Stand good on one leg first. Turn over. Down. Control it over. And up. Other leg. Stand good. Over. Down. Control it over. The toes up on the outside. Breathe in the arms. And out and sink down. Hands onto the ground. Come with the back up. And roll slowly with a round back up. Back into the backward shoulder. One more time. And down. Hands onto the ground. Come with the back up. And roll slowly with a round back up. Into the backward shoulder. Legs to the sides. Breathe in and out. And breathe out. In and up. Out, breathe in, close the legs, and in and out. This was for shortened hip training. Thank you very much, and until next time.